Okay, I think we can start. Uh, the past, this is kind of, let's say, journal club because Gia is going to comment of the claims of this paper. And the claim of this paper are rather important for us because if they were correct, the question is what would we be doing here? We had also the past week a talk of Ki-woon Choi on this same paper, and some of you were not here. So I know that Gia had, in one of his recent papers in September, he had a long footnote commenting this result. And that's why I asked him if he was willing to dig into his comments. And I'm very grateful to Gia that he accepted to give a second talk. No? The first talk was on Monday. So Gia, thank you very much.
Well,
and we are here to
thanks
listen.
to you. Yeah, it's absolutely, yeah. This is very important to clarify, obviously. We cannot just leave statements like that uncommented. And indeed, basically this discussion will be essentially explaining my footnote in my paper. Yeah, there was a talk. Unfortunately, I was not around. Yeah, unfortunately, none of these people are around to discuss. Okay, so what was the statement of the what was the point? Okay, the main point. The main point is that these people, they do computation. I mean, pretty straightforward one. I mean, obviously technical. But they have sort of question about the limits, okay? So there is the control parameters, there are two control, one control parameter, which is the ratio, but so there is a parameter n, which is the essentially the instanton number, okay? And the volume. And the volume, I think they noted by omega. And volume measured in the units of the vacuum energy density induced by instantons. And so this is as right dimensionality. So this is dimensionless, this is dimensionless. And then the claim was that there are two possible limits that one can take. And there is a limit when n is much larger than this. Essentially, you take limit in which n is infinite. First take infinite n, and then you take the limit with volume, with infinite volume. And this gives essentially the standard result that vacuum, there are theta vacua, and there is CP violation, vacuum, and CP violation. CP is violated by the vacuum. And there is another limit in which the opposite happens, okay? And this essentially, and in this case, they claim, and they obtain by computation, that the vacuum is CP conserving. So no strong CP. Of course, and if this were correct, obviously, would be extremely important. Okay, so in his discussion, I had a brief look at the presentation, which is online yesterday. Ki-woon Choi, he discussed this in great detail. So if you really want to go through the steps of computation and stuff, he's doing that, essentially, the essential point, okay? And his argument was, he basically agrees with technical part, the one that is presented. And his argument was that actually this is the correct limit, okay? And he had some arguments which imply that essentially n is correlated with omega, with the volume. And the reason is that in the dilute instanton gas approximation, you essentially populate volume by number of instantons and anti-instantons. They are far apart. So there is a typical size rho, which determines the size of the instanton, okay? And essentially the number which is permitted by the dilute instanton gas approximation is essentially this number, okay? So it's sort of natural number that you, so therefore, I think if I understood it correctly, his point was that because there is this sort of natural correlation between the instanton number available and n, therefore this is the correct limit, okay? Now, so therefore there is vacuum is CP violating, okay? Now, I fully agree with the last statement. Certainly, vacuum is CP violating. However, this still leaves a question because, okay, the argument that there is a naturally given value of n, I mean, yeah, it is a good argument to if you want to follow this limit, but still there is a question remaining. I mean, do the limits commute or they don't, right? So that's the question. And usually, when we do computations properly, typically limits commute, unless there is a discontinuity in the theory, okay? So then the question is there some intrinsic discontinuity in this case, or do the limits commute? But if the limits commute, then what is happening, okay? What is the part that we're missing out in this computation, okay? So yeah, I also, with the part of the computation that they are doing, I don't have any issues there. Of course, they are at the end of the day, if you check the paper, at the end of the day, for example, if you compute vacuum energy and things like this, the result in the second limit, there is some theta independent part and there is something horribly non-analytic in theta. But let's assume that you can interpret it properly, and so, okay. So there are these little questions here and there, but otherwise I don't have any issue with the computation. Now, my footnote was the following, that when we are taking limits and commuting the limits, and we are, let's say, interested in the vacuum structure of the theory, right? So here it's all about the vacuum. We want to understand whether vacuum is CP conserving or not. It is extremely important not to miss out the states which become vacua only strictly in that limit. Because obviously if you miss out those states, right, if they are states, so imagine the following situation that somehow, sorry, I don't know, let's plot it like this. Somehow you have states, and then there is a vacuum state here, and you are taking the limit in which all of these states become vacua, right? But for any finite value, they are not. So then you can very easily make mistake because you are focusing on the one which is vacuum all the time. And the other ones are left unattended. And then they come back and bite us because we are missing. And my understanding is that this is what is happening in this computation. And the three-form language actually is very useful for shedding light on this story, okay? Why we have to be careful with the limits. Yeah, let me go like this. Okay, so therefore, let me use this three-form language, okay? And first, let me illustrate very clearly why in the case of three-form, if we do certain computations there, okay, we regulate the problem and then take the limit, we can easily miss out the vacuum states, which are CP violating. Now, as I said, and three-form language, so in three-form relies on the fact, three-form understanding of the strong C problem relies on the fact that there is a topological susceptibility of the vacuum, okay? So there is a correlator. and this is constant and non-zero. And F tilde, this is essentially, this is field strength. So further, I can call it E. And this is field strength of a 3-form. In more conventional language, this is epsilon in nu alpha beta, d mu c nu alpha beta. And C is a Chern-Simons 3-form, let me write in conventional, nu alpha of course, this is trace. A is a gluon matrix. Okay. So this is Chern-Simons 3-form. And so from topological susceptibility of the vacuum, it immediately follows that the spectral expansion of 3-form, okay, has a pole at p square equals 0. I mean, QCD is a theory with a gap, and then we have non-zero mass all possible excitations of a non-zero mass. So there's a gap, and this is the field. This is the pole that is fully responsible for the vacuum structure of the theory. Okay. Now, and this can be easily seen. So in other words, this means that C as an operator contains a massless 3-form and then some massive excitations. Now, here, actually, it's not important. We can also add quarks to the system, heavy quarks. So I'm only adding massive quarks to the theory so that we maintain the gap. So correspondingly, suppose I now write down an effective theory, low energy effective theory, but keep track of everything, essentially, everything that I have at low energies, to all orders in operator expansion. Okay, so then what is the theory? So the theory, so from now on, I will also call the massless C4 part, which lives here, C, okay, not to introduce new notations. So there will be a part which is algebraic in E. E is the field strength, okay, plus all possible high derivatives. Okay, so part algebraic in C and high derivatives. Now, it is obvious that if I'm looking at if I'm looking for the vacuum, because vacuum must be Poincare invariant, the field E must be a constant in the vacuum, 0 or non-zero, but it must be a constant. Correspondingly, it's obvious that all this high derivative structure is completely irrelevant for determining the vacuum of the theory. And then this, of course, makes the problem very, very nice, because entirely the whole information is encoded in the algebraic structure of E, okay? And now if I write the equation of motion, if I do variation of the action with respect to C, with respect to C, of course I'm not doing variation with respect to E, variation is with respect to C, the equation of motion has very simple form. It's derivative from the derivative of K function with respect to E, and this must be 0. And of course, this is solved by arbitrary constant E, okay? So correspondingly, immediately we recover the conclusion that vacuum is, first, it contains infinite number of superselection sectors, because E cannot be changed since there are no charges, no light charges charged with respect to a 3-form C, okay? Correspondingly, there is no way to change the electric field classically or quantum or in quantum mechanically. And correspondingly, the vacua are labeled by expectation value of E, okay? And these are literally theta vacua, because E is a gauge invariant quantity, which is gauge invariant observable quantity. It's an order parameter of CP breaking, okay? So E, a constant. All right, so now this looks pretty rigorous, okay? Then the question is, how can I confuse myself if I'm doing computation with some kind of infrared cutoff, let's say, okay? And then are taking cutoff to 0, okay? In other words, volume to infinity, cutoff to 0. So let's do the following thing, okay? First, a very simple thing. Suppose you somehow, I go there? Ah, okay. Okay, so let's regulate the problem, okay? By the way, before I go there, from now on, I will use, instead of function k, okay, I will use k function. Okay, so first, we're not regulating a problem first. So I will use, for simplicity, I use E square, which is fully sufficient for illustrating the point, okay? And let me say a couple of words about the three-form, which is useful, will be useful, okay? Now, the three-form field strength, so we can also introduce field strength with indices, simply another four-form field strength, right? Anti-symmetrized, so I will assume that everything is anti-symmetrized. So we can write in these notations, and okay, essentially E is just a Hodge dual of this, okay? It's just epsilon mu nu alpha beta, E mu nu alpha beta, okay? Now, if I write down the equation of motion for C, right? So in this language of E, the equation of motion is this, okay? Now, there is a gauge redundancy in C. So let's investigate the properties of C. So C has gauge redundancy, obviously, which is, so gauge redundancy changes by as an anti-symmetrized derivative of a two-form. So let's call this two-form. Okay, I already used this omega. Let's call it mu alpha. Okay, a two-form. Now, there is a redundancy for arbitrary two-form, obviously, okay? But there is also redundancy of the redundancy, because there is a redundancy prime, because omega nu alpha, I can also change by an arbitrary anti-symmetrized derivative of a vector, okay? And there is redundancy of the redundancy of the redundancy, because vector also redundancy prime, double prime, because the vector I can change by addition of a scalar. Okay, let's call it beta, derivative of a scalar. Okay, so now why is this important? Because this is important for counting the number of degrees of freedom, because this tells you that because of this redundancy, the gauge parameter itself, okay, psi, essentially contains three degrees of freedom. So the power of this psi is to kill 3 degrees of freedom, okay? So 3 here. Correspondingly, these 3 can be subtracted with 6 degrees of freedom in omega, which is an anti-symmetric two-form, right? So here we have 6 minus 3, 3. And correspondingly, these can be used to subtract 4 naive, out of 4 naive degrees of freedom, 3, okay? So the redundancy. And so 4 minus 3 is 1. Now, using this redundancy, I can bring, see, for example, in transverse gauge, okay? Okay? And bringing C in the transverse gauge, of course, simplifies this equation of motion. At the end of the day, the equation of motion simply becomes box mu nu alpha. But then on shell, there is still remaining redundancy in omega, okay, because I can still shift omega by a vector as long as that is on shell, okay, and vector by this. And correspondingly, I can eliminate further degrees of freedom. So correspondingly, I'm left with 0, no degrees of freedom, okay, for omega. No for C, no propagating degrees of freedom, okay? So C is a very interesting object. Because, why it's interesting? Because it's a field. It produces correlators, obviously. If you couple it to something, it will produce a force, okay? But it doesn't have a propagating degrees of freedom. It's sort of pure Coulomb part, okay, of the story. So it's like a Coulomb part. So C actually is very similar to, and there are a lot of similarities with Schwinger model in 1 + 1 dimensions. So in 1 + 1 dimensions, electric field has literally these properties. If you don't have, if it's massless, then it has no propagating degrees of freedom, okay? All right, so we have this story with C, and so C has no degrees of freedom. Okay, fine. Now, it's okay, I move now here, right? Okay, so now with this knowledge, we are equipped with this knowledge. Let's regulate the problem, okay? So now you regulate the problem by, let me put an infrared cutoff, which remove the pole from 0, okay? So I remove pole away from 0, and then I do computations, whatever I want, and then I take the limit back, okay? All right, so therefore, what I do, I say that the pole, I introduce a regulator, mu, let me call it mu, and so now I have a massive pole, okay? Then later I will take this mu to 0. Now the massive pole means that now I'm dealing with a massive 3-form, okay? And correspondingly, the equation for the 3-form will change. First of all, this means that effectively what I'm doing, I'm effectively adding to the Lagrangian a mass term of C, okay? Now, I need to change notations because that's very important. Because since we are dealing with gauge theory, as you know very well, whenever I move gauge field away from 0, the pole, okay, I may introduce new degrees of freedom. Usually, that's what happens. So therefore, in order not to confuse this with the old C, let me put a bar on top of this so that now we remember that C has a bar on it, okay? That C corresponds to a shifted pole, all right? Okay, so now let's investigate this theory, sorry, C square, okay? Now let's investigate this theory. Now if I write down the equation of motion of this theory, the equation of motion, okay, here I'm just assuming that they're proper coefficients, which I can rescale. Okay, so now, of course, there is no longer a gauge redundancy. There is no longer gauge redundancy in C bar, okay? In C bar, obviously, because there is a mass term. By brute force, we put a mass term. And correspondingly, I can no longer use this gauge redundancy to eliminate the number of degrees of freedom from C. However, there is a constraint, very similar to Proca constraint for a gauge field, because if I take divergence of this equation, okay, let's say with respect to alpha, the first term vanishes because it's anti-symmetric, and we get a constraint okay, so we get a generalization of Proca condition on C, okay? And now if you count number of conditions that this gives, we have to remember that alpha, B, and gamma, they are anti-symmetric. Effectively number of conditions this gives, it leaves 1 degree of freedom, okay? Out of naive 4 of C, because now there's no gauge redundancy, so naively C would carry 4, but actually there's only 1 left, okay? So there is 1 propagating degree of freedom, which means that This is important because this means that whenever I shifted the pole, I have endowed a 3-4 by a propagating degree of freedom, okay? All right, so very good. So now let's investigate this theory, okay? So now imagine that I want to understand the vacuum structure of the theory. I do this, and then I take the limit when mu goes to 0, okay? And let's see what happens, right? Let's see, maybe, how should I move? Back up? Or? Yeah. Okay, so, yeah, so now, so what are the solutions? Now, certainly there is a vacuum solution. There is a vacuum solution with, so the only solution with E equals constant, the only solution is the 0. This is the only E equals constant, okay? Correspondingly, in this theory, I will immediately conclude that vacuum is CP conserving, okay? Well, because of this equation, essentially, this equation has no solution, this equation. Because using this constraint, I can write this equation as box C alpha beta gamma mu square C alpha beta gamma, effectively. And this has no solution, no solution that would give me a constant E, because E is the one that I have to worry about, not C, observable, other than 0, okay? So that is the only constant solution is 0. Correspondingly, since vacuum has to be E constant, because it has to be Poincare invariant, the vacuum in this theory is unique and it's CP conserving, okay? By the way, remember from my talk that effectively, this is effectively what axion does, in particular in gauge axion case, the Higgses, this thing. But here I'm not asking about axion, I'm just saying, suppose by brute force, I just put a regulator, then I take it back, okay? So, now, however, there are solutions in this theory. These are precisely solutions that become vacua in the m going to 0 limit. They are not vacua in finite m limit, okay? Finite mu limit. So there are solutions in which C and correspondingly E is, let's write directly E, is oscillatory. So in other words, let's write it like this. Let's take the cosine. Let's take the cosine solution. I mean, there are oscillatory solutions. In particular, I'm choosing cosine, okay? So certainly there is this solution of this equation of motion. Because, for example, you can choose C to have, let's say, 1, 2, 3 component and time dependent. And then this equation simply becomes an equation of the oscillator, C plus mu square C 0. Okay, so this gives you oscillatory solution for C and gives you oscillatory solution for E, okay? And, okay, so for this solution, C would be something like lambda square over mu sine mu t, okay? Okay, so now, these solutions, obviously, they are CP violating. Of course, because the order parameter that breaks CP is non-zero, but they are not vacua. None of those is a vacuum, obviously, okay? So they are not vacua. However, now if I take, so therefore, now if I do the following order, I say, okay, let me regulate the theory, and only focus exclusively on the vacuum state. Obviously, if I focus exclusively on the vacuum state, all the solutions are missed out because none of them are is a vacuum state, okay? Correspondingly, I will conclude that in this theory, for arbitrary value of mu, vacuum is CP conserving, right? Then I take the limit when mu goes to 0, and I conclude that vacuum is CP conserving. Why? Because since I started with finite mu, theory landed me on one out of infinitely many solutions, all of which become legitimate vacua in the limit when mu goes to 0, okay? Right? So in the limit when mu goes to 0, all of these solutions are solutions with arbitrary constant, and these are the ones that become theta vacua, okay, in that limit. All right? Now, let's make it closer to the quantum picture, in fact, okay, the story. And let's introduce also n, okay? Slightly sort of a dual n, but it doesn't matter, so here we have n. And then we go to the conventional language and translate this in conventional language. So this is the sequence. Okay, so I guess I can probably use that. Lambda there for you is just an integration constant, right? Yeah, lambda is an integration constant. Right. I brought it lambda actually if we really want to make full contact with QCD, at least for small values of theta, essentially this is lambda square would be QCD scale, and so this would be QCD, and this would be theta. So this is the dictionary. Okay. So for small theta, of course, in reality k is the inverse of the periodic function, but that doesn't matter. Okay, so let's introduce quantum. Let's introduce. Of course, vacuum are classic. Obviously, vacuum solution is always is mapped on the classical equation. But here for finite mu, and of course this you can do in finite volume. There's no problem. So for finite mu and finite volume, or even in infinite volume, what would be the quantum description of this? Now, quantum description of this is very simple. I mean, it's standard. It's as usual. So, quantum underlying picture. Okay, so C as any other field. Now, C with propagating degrees of freedom. C, as usual, has the structure of a quantum field, okay? Okay, let me not factors of 2n normalization, but important factors, let me temporarily restore h bar, temporarily, just to illustrate the point. So h bar enters here. Volume, let me call this volume V, although they call it omega, but it doesn't matter. Since it's a different language, let me call it V. Okay, then there is omega, okay, oscillation frequencies, exponents, right, and creation operators with of corresponding polarization. There's one polarization only of A. But since I am landing on oscillations of coherent oscillations with only time dependent, okay, essentially the non-zero momentum modes are not important. Of course, in general, there is an expansion in all possible possible P structure, okay, plus Hermitian conjugated. But non-zero modes are not important. So what is then this field, classical field? As usual, this is, by the way, in this approximation, it's just exact. The representation is exact. It's a coherent state. So E, classical, this E. This is an expectation value of operator E. I mean, operator E, of course, operator E is just derivative of this, time derivative from there, and so this is as, okay, let me ignore non-zero momenta. So then we will have zero momentum mode, zero momentum frequency omega. So omega, h bar omega is mu, okay, essentially, all right? If I translate in quantum dictionary. So, so this would be h bar. The structure would be the relevant component from here, the zero mode, right? H bar omega v, okay? And times exponent with some coefficient here, and then creation operator, of course. And the field is a classical field is an expectation value of this. So on a state, and on a coherent state, okay? On a coherent state, which now the coherent state is described by coherent states are the ones that are most classical because they minimize uncertainty relation. So it's a coherent state. Let me call it N. So here notation, I'm introducing notation, is that N will be a complex because coherent state has a complex parameter. So the modulus of N will be an occupation number. So N is just a displacement operator with A0 plus N star A0 acting on the vacuum, okay? I mean, this is completely standard. It's like here picture is extremely simple. You have one oscillator only with oscillation frequency, where is this, omega, which is given by the mass, no momentum modes. You create coherent state and you take expectation value over the coherent state. Now, as you know very well, coherent states are eigenstates of the destruction operator, okay? So effectively, the expectation value of destruction operator is square root of N. So basically sorry, it's not N, it's square root of N. Okay, I had to introduce more notations, but let me introduce a notation. So there is some thing, let me call it F. Oh no, F is not good. Let me call it L. And L has a modulus, and the modulus is square root of N, occupation number, and then it has a phase, some phase, theta. Let's call it alpha. Okay. Too many notations. Yeah. Anyway, so the expectation value is this times the phase. Okay. So this is the square root from the expectation value. And so now this captures the structure, which is beautiful as usual when you go from quantum to classical. This tells you that we get that the classical field has a structure h bar omega, which is essentially mu. Now we can write mu, N over V times factors which are not important. This is the important part. Okay, so now let's write it here. So in other words, in the quantum language, E is this structure. So let's make proportion. So the classical field goes as mu times the occupation number and volume. Now this tells you everything. This tells you that if I would first take volume to infinity and keep occupation number finite, n finite, okay, and mu finite, I will only get a Sipping conserving state, nothing else, all right? Okay, so, and the correct classical limit when I take mu to 0, now if I want to keep classical solution finite, okay, the amplitude of the classical solution finite, E, right, it's obvious what I have to do. I have to keep this combination finite, all right? So in other words, n has to increase as volume divided by mu. Actually, it's stronger than the volume in this case, okay? So n shoots up, okay? And so then, of course, you take this to infinity. And this is the correct classical limit. And in this classical limit, of course, you recover all the CP vacua, okay? They are not going anywhere, all right?
Some of this was the argument for keyboard at least at the end. Like not itself, but the idea of
Well, yeah, I mean, I think if I understood his arguments correctly, I agree with the fact that, so, I mean, I don't know, you should ask him, but I think that it's not obvious that limits do not commute. It's just you have to keep track of those states that become vacua when you take limit. And I think, so in their paper, they are ignoring those states because they are only focused on the vacuum. And obviously, as we have seen here explicitly, if we only focus on the vacuum, we will always get CP conserving one. So, yeah, so from I understand Kivun had a slightly different argument. I don't disagree with that. You mean this, whether this translates as his? Yeah, so, I mean, yeah, in other words, in certain sense, yes, but, okay, it was not very explicit in his discussion. This was not very explicit. He was saying that there is certain correlation, but here what I'm saying is that I'm not saying that you necessarily have to keep this. I'm just saying you have to have this in mind when you're taking the limit. There is no problem if you want to take the limit where you take first volume to infinity. You should remember that there are states which are also come from infinite n. That's all I'm saying. I'm not saying that. So I don't think I disagree with him because at the end of the day, I think his conclusion also is that of course there is CP violation, but somehow, yeah. Now let's as a final sort of connection. Let's try to go to the conventional language and see what is the story there. Essentially, this was already covered in Choi's lecture, but sort of let me a little bit add a little painting from a different angle. Okay, let's see which one is. Yeah. Sorry, there is an order in which I have to go, right? So there was some clockwise. This is okay. This is good. Okay, I'll sacrifice this one. Yeah. Okay, so now, here in a sense I finished the language, C language. Now I try to sort of add a little bit to the conventional language, okay? Now in conventional language, what is the story? So you have a Hilbert space, right? So in theta vacuum, what do we have? We have Hilbert space, and so the story is, right, that we have vacua with certain winding number, right? The states with certain winding number. That's the whole point, that they are not vacua. But these states, they are not eigenstates of the large gauge transformation operator, okay? And correspondingly, these states are not good vacuum states. And instead, the good vacuum states are the ones that are eigenstates of the large gauge transformation operator, and these are usual theta vacua, right? And this, we take the okay, so these are the theta vacua that are, okay, so now, so in Hilbert space, you have this vacua with these states with different n, okay? So you have these states, all right? And out of those states, you are making vacua. Of course, remember that to really make a good vacuum, this requires an infinite number of those, okay? Now, if I truncate, if I say that I limit my integration instead, imagine that I limit my summation from some minus n to n, okay, no matter how large, this is no longer a vacuum state, okay? So the truncated theta truncated at some n, this is no longer a vacuum state. Okay? So, in other words, when you are doing a computation, that's perfectly okay to limit winding numbers, okay, and also to limit the transition. So remember, this is what is happening in their computation in dilute instanton gas approximation, right? In dilute instanton gas approximation, you have gas of instantons and anti-instantons, and there is certain a certain total number, okay, nu, nu, which changes the topological number of the state, right? Now, if you are limiting nu, okay, effectively what you are doing, you are limiting your exploratory capacity of the Hilbert space. Because obviously, if nu is limited, you can no longer explore states that are farther from you in the true real Hilbert space, okay? So effectively, this is what happens. So in other words, what happens is that if you are limiting transitions by finite nu, if you are an observer, right, and you simply start with certain state, let's say you start with a state n equals 0, okay, and you let your system evolve. Someone prepares you in n equals 0 state. N equals 0 is not, of course, is not an eigenstate of the Hamiltonian, obviously, and it will evolve, right? But if you are limiting capacity of the instanton gas, let's say, to have sufficiently large transitions, effectively what you are doing, you are limiting the Hilbert space. So this is what translates as a limitation of the coherence in the C language, okay? So in other words, you are effectively creating a cutoff, okay, which they do, obviously, and cutoff is n. But this cutoff, of course, what it does, effectively, this cutoff is what creates the mass gap in the description of the C form. Now, it's very, okay, it's very tempting to do this analogy. Let's see, yeah, okay, you can. I mean, the analogy, okay, I would say, imagine that you have a quantum mechanical particle in the periodic potential, right? Right? So, and we know that there is this analogy in this instanton building this like Bloch waves and etc. The thing is that if you limit the number of the volume of the potential, or which is equivalent if you limit if you artificially truncate instantons that could give you transitions between distant numbers, you are creating effectively an infrared cutoff. And the system, of course, evolves very differently. And among the infinite number of waves of this state, coherent states, you're only seeing, you will see that those are not vacua, so you don't pay attention to those. And then, of course, you land on the CP conserving vacuum. But of course, at the end of the day, if you take the limit, all those states come down, and they are there. They didn't disappear. It's just because you truncated your discussion, because of that, you missed out this good would-be vacua. So this is my interpretation and understanding what is happening in this story. So, yeah. Well, yeah, that's why this intuitive part, I left it for the end. Because intuitively, this is what happens. So let's think in the following way. So as you know, okay, a good way to think about instantons, right, is to think of you know that the instanton solution, if you lift up in 1 dimension higher, it's like a soliton, right? Okay. So instanton in 4 dimensions, if you mentally lift the theory in 1 dimension higher, is like a soliton. Okay, so it's a monopole type soliton solution. Okay. So now, if you think QCD being a slice in this fictitious, completely fictitious high-dimensional space, but that's a very good way of thinking about instantons. If you think of QCD being a slice in fictitious fifth-dimensional space, then we live on this slice, and this slice has certain winding number n, okay? Right? Why winding number n? Because this slice has this integral of c, right? And on the boundary or as a volume integral, and so it has certain winding number n. Now, what is happening is that instanton you can view as a monopole that passes through this, okay? Comes from extra dimension and tunnels through, literally. In this case, you see that you have this shower of monopoles going back and forth, okay? And so correspondingly, you have arbitrary changes of the number. Okay, so now imagine you have a volume which is perfectly sufficient to accommodate huge number of these instantons, okay? Of this gas of these monopoles that goes through. By the way, here this argument is independent of dilute gas approximation. That's not so important for that. But let's stay within dilute gas approximation. Even with dilute gas approximation, you have plenty of these guys can go through without touching each other, okay? But instead, what you are artificially limiting this flux. Of course, that's the equivalent of truncating a Hilbert space that is available for you for any finite time. Because, you know, to explore Hilbert space takes time. You need instantons to go from n to n plus m, right? Right? So therefore, if at some t equals 0, I start, someone prepared me in the state n equals 0, let's say, right? Of course, this is not a vacuum state, and this is not even an eigenstate of the Hamiltonian. This state will start to evolve, all right? But it evolves because immediately you have shower of these monopoles that go through. And now if you are limiting this shower artificially, which is not limited, this is precisely truncating. This is precisely truncating. I mean, effectively this is equivalent to truncating the Hilbert space, availability of the Hilbert space. That translates as creating this infrared shift of the pole from p square equals 0. Okay? I mean, in the free-form language. I mean, free-form language doesn't need this explanation. It speaks for itself. But I'm just saying, if you want to make this connection, you don't even need to mention free-form. This is what's happening here. You are creating effectively, you are creating a cutoff, and this cutoff, certain states that otherwise would be correct vacua are not vacua, so are not paying attention to those states. This is what's happening. And then they come back as vacua when you take the proper limit. So therefore, I mean, I think it would be a good exercise to sort of, in their language, so that if they can, so that they keep track not only of the vacuum values, but also expectation values over all possible coherent states, then my prediction is that this is what they're gonna discover, that all the theta vacua, they perfectly nicely materialize in that limit. Mm-hmm.
Then what this means that if you don't allow for larger n, you're limiting the monopoles that go through or the instant.
Yeah, right.
And therefore you can never build the full vacuum that contains all of them, right? So then any possibility that you're building out of a limited number of n will necessarily be an excited state and not the true vacuum, and that's why you say that that's a cutoff, because you have more energy than the true vacuum.
Yeah, except also the consideration of the time in this problem, the way this was sort of a toy problem, right? It's a probe situation. I'm just saying, imagine what would happen in two cases, a true case and this truncated case, right? In both cases, we can prepare a t equals 0, n equals 0 state. There is no problem. Someone can prepare it for you, okay? So now the question is, what kind of time evolution do you observe, all right? In the truncated case, your capacities to explore Hilbert space are limited. So effectively, again, I'm saying this is, effectively this translates as limiting the Hilbert space, okay, for sufficiently long time, okay? Now, of course, time scale is involved because time scale, there is a time scale associated with this limitation, right? And correspondingly, so that is important. But immediately, that's what effectively, and in the C form language, that's effectively creating a mass gap for a C form, okay? Yeah.
What happens if you regulate the theory, putting it in a box with periodic boundary conditions? Would you still have a completely different space?
You mean no, just if you just limit it, that's precisely the point I'm trying to make, that if you limit the volume, but you allow all possible n, then there is no issue. You will get a correct vacuum structure. Then there is only one parameter. You can take volume to infinity and that's it. There is no question about limits because finite volume, infinite n, of course, for infinite n, you have to go beyond the dilute instant on God approximation. But the C form language doesn't care about in which approximation you work. It's like so let's say someone can compute this, everything, right? No problem. You can have finite volume, arbitrarily large winding number. Then theory itself will tell you, because then you will compute and you will see what happens with instantons when they start to overlap, and then there will be some answer. That's okay. There's no problem with that, okay? So, and then you take volume to infinity. And yeah, I don't think that there will be any question there. So here they are taking the opposite, from what I understand. They want to precisely explore the opposite. When you have available n, plenty, but you limit yourself artificially. So you are limiting available, the system wants to transit, and you are saying, no, stay there. And then you are taking the limit, and then you are taking second. So yeah, this is what is happening in this case. And of course, when you are doing that, I think it's still okay as long as you keep track of those states that you have excited. But by limiting n, you are certain states that would be vacua, you are promoting them into time-dependent excited states. This is what is happening. Look, it's very, in quantum mechanics, if I have two potential wells, right? The quantum mechanics with two potential wells. If I have only two, what happens? If I start with one, I have oscillations, right? Back and forth. So I go back and forth. If I have more, there is always a spread of function, right? Now, always if I effectively ignore instantons, certain set of instantons, okay, I will effectively ignore states that would otherwise be sort of reasonable vacuum states. Now they will become time dependent. Because it's like, I don't know, if you think in terms of Hamiltonian, it's like artificially subtracting elements from the mixing elements from the Hamiltonian. You say, okay, I only want this, then later I will put them back. The problem is that when you put them back, you have to keep track of those eigenvalues that you have ignored because you decided that those are not the vacuum states. Okay? Yeah.
What I missed is why your vacuum defines finite n, but with theta equals 0, so without the phase factor,
Yeah.
which is still non-invariant under large cage transformation. But why this is the one that survives? That also should probably go, isn't it?
No, I'm not saying that this, so let's see. So I'm not necessarily, my statement was not that the state survives as a vacuum. What I was saying is the following, that once you do this, there is a vacuum state, whatever it is, okay, which is CP conserving, okay, which then, when you take the limit, evolves into theta equals 0 vacuum.
So it's not the state where I put the 0.
Naively, I would say that yes, that's the one to, certainly it is the state with theta equals 0 to which it evolves when you take the limit. Whether for finite n as you said, I mean, for finite n, this is just even if I truncate this, the Hilbert space here, obviously this is no longer a eigenstate of the operator, obviously. Yeah, I agree with that. Yeah, but that's. I mean, that simply means that, for example, in this.
So what I mean is why this argument, which intuitively I can follow, I understand, why this argument is preferring the value zero. I cannot see that.
Oh, you mean, okay, so the argument, so the question is why this truncation prefers value equals 0. Yeah, because okay, all right, okay, I don't know if this, okay, in the three-form language that is obvious. Why? Because that is the only one which is, okay, here, the way I would say is the following, that the theta equals 0 is the most symmetric one, right? And so, because it's a superposition of all with equal weights. So it, for example, if I think, I don't remember now with the block in the case of this n potential, maybe someone can look it up, but for example, in the case of two with potential wells, the states that are true vacuum states are plus minus, not with some relative phases. So something similar is probably happening here. But I mean, this is checkable. I don't know. I just don't remember if someone checks what happens in the case of periodic potential with theta, whether theta equals 0 is still a vacuum state or what kind of state. No, it's very important. Right. So they are not truncating. I'm not saying they are truncating this. They are not truncating. They are truncating the ability, the instanton number. Okay, not this. No, that's not, this is. They are not. At least I don't see explicitly that they truncate this. They limit transition power of the instanton gas. That's what they truncate. And what I was saying is that for a while for certain time scale that limits exploratory possibilities of the Hilbert space. Okay, I mean, again, this discussion, this is just some intuitive interpretation. Okay, so deconstructing my footnote was about three-form. Okay, so this is the sort of intuitively how I understand why you have to, yeah.
So I'm not sure if it makes sense. But can you make a constant picture without regulating mu?
If we can make picture.
Constant picture without introducing regulated mu.
Yeah, without introducing mu. I mean, yeah, no quantum picture. This picture is valid for arbitrary mu. It's just so for when you take mu to 0, of course you have a massless field in that case. Exactly. Then it's a limit. So that's usually the story. If you think of if you think of a massless field, right? Or Schwinger or constant electric field. So you can think of the constant electric field in normal Maxwell. You can.
Just quantizing like an instanton.
You mean here?
Over there.
No, here, that's the whole point, because free-form language doesn't care about instantons. That's the power of this language, because free-form language tells you that you can have whatever source, whatever states, whatever you want, that saturates this correlator. Well, I erased it. Well, yeah, at the end of the day, n emerges, yeah, but that's not, there is no, in C-form language, you see, C-form language tells you that there is a correlator. C-form language tells you that there is a correlator and there is a p-square pole here. C-form language doesn't tell you how you obtain this operator. By the way, C-form language, by the way, if you go, there is still this thing. It's true that the only computation-wise, the ones that we know that contribute are the instantons, that we can do computations with instantons. But for example, if you go to large N QCD, not this N, but number of colors QCD, they are with an Veneziano mechanism of generation of the eta prime, you remember. So there is no reference to instantons. I mean, there's not a single reference. Actually, there is this also this thing that the eta prime mass goes as 1 over n as opposed to exponent minus n. And okay, so let me enter there. But the key point is the following, that you have certain states that saturate your correlator. I don't need to know what they are. As long as this correlator, so this can be instantaneous, can be something else. Can be global tower, can be whatever. So in that language, for example, in Witten language, there is no instantaneous, it's just a global tower that contributes in that language, right? So in trivial language, yeah, it's just everything translates to this correlator, and that's it. And then all the physics that somehow regulates your problem, if you want to regulate your problem so that you make it vacuum temporarily CP conserving, as long as that physics is Poincare invariant, it boils down to shifting this pole, because there cannot be anything else. Because the only Poincare invariant deformation of three-form theory in order to land on a CP conserving vacuum is the shifting of the pole. There is nothing else we can do. Okay. But maybe I departed from your question. So so your question was about instanton number. Yeah. Then I sort of interpreted this intuitively in this language. Why? How do I see these limits? Why they have to be? I mean, my message is very simple. My message is the following, that they should have kept track of states that are expectation values of a coherent states that are not vacuum states, period. Up until they do that, and they take proper limit, they cannot claim that vacuum is CP conserving. There is absolutely no that statement is not trustable. So that's the main message. That's the main statement, yeah.
So which calculation you have to do in order to show this in the language?
Well, I mean, the same calculation they did, except not compute expectation values, not only vacuum expectation values, but also expectation value over certain candidate Poincare non-invariant states. Okay? Now, one has to sit down and think. It's an interesting question. I mean, also, I don't know how doable this is, but okay, the answer I anticipated. Yeah, for sure there will be states that materialize as theta vacua when you take limit properly. Now, of course, as I said in their paper, also Choi mentioned in his discussion, yeah, the answers they get are slightly, okay, requires some gymnastics to interpret, because they get non-analyticities that usually require some interpretation. So, okay, there can also be issues like that in their paper, but I'm not entering there. Okay, but my point is that when you're taking a limit and you always focus on vacuum expectation values, you are missing the states that are not vacua except in the limit. And that's it.
Well, yeah, thanks a lot. Thank you very much.
Yeah, that's one thing I'm confident. Yeah, one thing I'm confident about. Yes, that's right. That's absolutely correct. In fact, there is a toy model, a low-dimensional toy model, in which we also have instantons, like one plus the 1 plus 1 dimensional Higgs, for example, 1 plus 1 dimensional Higgs theory. All right, so there we have instantons, and no, 1 plus 1 dimensional Higgs theory, for example, right? There we have instantons, and there actually it's easier to track this probably. So one can maybe do a computation there. And, okay.
Yes, and I think it's also nice to know that if you do things properly, okay, the order of the limit it should be.
That's what I would expect. Yes, that the order of limits should not matter. If the
properly, because sometimes it does matter. We know, like, you know, of cases in physics where it does matter.
No, no, of
Like,
course, of course. Right, right, right. When there is a when there is
not one of those cases.
when there is a discontinuity. So for sure, sure. So now, as we know, even in that case, and when the Sakharov case, of course, I mean, limit matters in the sense that, yeah, so.
On Minkowski, I think if you change background, maybe sometimes it disappears even.
Yeah, but that's a separate story. But you see, in Adam Eltman Zakharov, what they are doing, they are taking. So in other words, if you take a full quantum theory, then there is this longitudinal polarization of the graviton if it couples to the trace of the energy momentum tensor. Of course, the thing is that you have quantum corrections from the source, and they may somehow do something with these polarizations and this kind of stuff in that limit. But in any case, I mean, yeah, there are cases when there is a discontinuity, for sure, absolutely. Here, I mean,
Probably not.
yeah, because usually discontinuity is there when the limit can have different number of degrees of freedom. Okay. Now, if there would be discontinuity, suppose they do this computation and you still discover discontinuity, then somehow it would be equivalent of essentially introducing a new degree of freedom in the theory. Because this is what happens in fundamental Zakharov, right? Because there is degree of freedom, and that's why it limits to not commute, because, you know, yeah, from the other way around. So something like this should happen, probably. Then this would mean that essentially they have some axion-like degree of freedom that doesn't decouple. Okay, so then it could be the conclusion could be, but I don't expect that. I think that because I think situation is more straightforward.
In any case, you show that the limit. I mean, your argument is the limit is not done properly. So before you
Exactly,
limit
exactly,
properly,
yeah,
you cannot
exactly. So my point is, my main message is that the limit has to be done properly. That's what I'm saying. Yeah.
But then I didn't understand your answer to the question of Enrico, because let's say we find that argument convincing and that you're missing some states and therefore the limit